quite a lot of you. Thanks, man. I observe. Yes, that's a science thing, observation. So there's a tradition at GraphConnect. Emil gets the opening keynote, and he gets to say all kinds of fun things and kind of perk you up for the day. And I get the closing keynote, and my job really is to get you out of the building. That's really my task here. But normally, we have the kind of gentleman's agreement that Emil will make a few cheap shots at me, and then I'll retaliate with undue force in the closing keynote. I don't know if you noticed this morning, but Emil decided to go all professional. Not a single pop at anybody. Not even me. And I'm an easy target. Which means I'm going to come off as a total dick for the next 40 minutes. I'm literally going to accost my boss in public for the next 40 minutes, and as far as you guys are concerned, he's done nothing to warrant this. So, great, awesome, there you go. So what we're going to talk about? We're going to talk about the future of where we're going in the graph space. It's like, you know, it's going mainstream. It's becoming a really, really popular space to be. Now, Emil, this morning, really had all of the fun bits. He's the captain of our enterprise OSS. I guess that makes it the OSS Enterprise Grown. So he gets to say all the fun stuff, right? He's like the Silicon Valley CEO, right? So he's going to get a turtleneck one of these days. It's all prophesized. Right? He gets to say fun. He's like, we're going to announce Open Cypher, and we're going to make sweet love to Spark. It's all like, it's you know. So that's great, right? I don't begrudge the guy that, you know, he deserves it at some level. But then, damn it now, stop, you're going to get us fired. My old boss is here. He's actually only about 30, but he looks like 90. It's a tiring experience. So the problem now with the closing keynote is that you've had the exciting guy with all the announcements and the flamboyance and whatnot, and now you've got the science guy. That is my only option. I'm going to have to science the shit out of this in order to even get a tenth of what he got this morning. So, as an aside, and I know you were all wondering, you're thinking, who sponsored your wardrobe? Huh? I know there are a few of you that were a little bit, hey. And of course, it's Rick van Bruggen, sponsored by Belgium's leading English language Neo4j textbook. Love you. Thank you for the wardrobe. So thanks, Rick, or Poirot, as we know you. You all have them, right? It comes with your passport. It comes in the back cover. Thought so. Anyway, so thank you for the wardrobe, and your book is brilliant. And all right, that's cool. Oh, hey, Emil. Yeah, you did, didn't you? You wrote a book too, of course. I don't want you to feel left out. You wrote a lovely book too. No moustache for you, though. Notice. No, it's all good. So anyway, what are we going to talk about? What are we going to talk about? We're going to talk about the graph space. I've got three things that are on my mind. I've got that I want to just get off my chest. So this is partially closing keynote and partially my own catharsis. So I can't really afford therapy. You're it. So I've got three things that I want to grumble about to you and kind of see if we can set a reasonable course through the interesting and emergent graph space. So I want to tackle the notion of single and multimodal databases. I want to talk about online transaction processing versus analytics and how that plays out in the graph space. And I want to talk finally about the notion of native and non-native technology being applied to storage and query of graphs in particular. That's not working, is it? Just sorry, I know it's really embarrassing. I should be a professional speaker. Something's just a bit wrong with my laptop here. Sorry. Talk amongst yourselves for a moment. I'm just gonna change the locale. Okay, that seems all right. That feels like that solved a few bugs. Just quick test, just to make sure that we're back on common ground. These are chips. These are crisps. He's already mad at me for disobeying the cardinal rule that we all speak American. Jolly good. So now we're back on familiar turf. I'm going to talk about the graph space. We're going to take a journey through space and time in the graph space, going who knows where, hence the enigmatic title. We're going to look at what it means to have graphs in a single model, in a Neo4j style database, or indeed in a multi-model, in a kind of polyglot style database. We're going to look at what it means to do online transaction processing in graphs. My ex-boss is a transaction genius. I'm going to be so embarrassed talking about this in front of him. And we're going to talk about what it means to do analytical workloads inside graph technology. And then finally, we're going to talk about that native versus non-native stuff. I think that's very, very interesting computer science going on there. It also happens to be the stuff that my team is working on over in the old world. So let's start with the single or multi-model stuff. Anyone ever heard of Unix? Just evidently, a small number of people in the room have heard of Unix. The quality is dropping as the quantity increases, evidently. I'm guessing that some of you are just a bit shy because there's like this random limey ranting on the stage. I'm guessing most of you have heard of Unix. There's a thing that underpins Unix. There's a philosophy that I think is quite appealing to those of us in engineering and development, and it's do one thing, do it well. Yeah? All of those, like, Terminus or Unix tools are all optimized to do one thing and do it well. And then from that fundamental foundation, you can then build sophisticated workflows by chaining those tools together. I rather like the idea of doing one thing well. Neo4j does graphs. That's what we do. We don't try and be all singing, all dancing, all things to all people. We do graphs, and we do it well. I think that is what we've strived to do over the years, and it's what we're going to strive to do in the coming years. But that's not necessarily the only point of view. I mean, you may say that some things that I have aren't graphy. Maybe I need other data kit to deal with those. Maybe, in fact, I want a mixture of technologies. Maybe, or I need a single technology that can handle graphy and non-graphy data. Maybe. I mean, I just sat through Karen's excellent talk, and she made the point that often your data is screaming graphs anyway, and you're not listening to it. So let's see what happens when we play this forward. In terms of, do I go with a single model or a multi-model technology? I would say this. I would say that graphs are such a flexible model. They are a model that can tolerate or indeed embrace many, many different domains, many different kinds of data, that they're probably all you need. You've got a document problem? Sure, but documents are just trees, and trees are just simple graphs. You've got a shopping list, or in fact, maybe you've just got a shopping basket that you then want to turn into retail trends. Lists are graphs. Train lines are graphs. Your lovely road network with this bridge over here that's very distracting as a speaker is part of a large graph. Spreadsheets are graphs. Now that is really, really weird, because spreadsheets are the archetypal square. It's a grid, not a graph, Weber. Go back to jail, do not collect 200, except no, even spreadsheets are graphs. Of course, we have relationships around neighboring cells in a spreadsheet, but where spreadsheets get very graphy is when you start using functions to refer to other cells in that spreadsheet. Those spreadsheets are a graph. In fact, Felienne Hermans, who's a professor from the Netherlands, actually will take your spreadsheet, she will decompose it into a Neo4j graph and tell you where all the bugs are, empirically demonstrating that even boring square spreadsheets are graphs. And it's my thesis that practically anything can be modeled conveniently as a graph and queried efficiently in Neo4j. So I've been wondering about this. I've seen a lot of vendor hype going on out there, and I've just been thinking, well, given that most common data structures that I work with are effectively one or other variants of graphs, why would I get excited about things that claim to do multi-model? It's like, well, the graph already does multi-model. It does lots of different graphs. Even things that you might traditionally associate with more specialized databases, like things like range queries and so on. From Neo4j 2.3, you do range queries in Neo. But that's not the be-all and end-all of it, because these range queries tend to be jumping-off points for even more sophisticated graph analyses. In this case, it's a really crap graph analysis, because it's like no one called Jim has prepared properly for his GraphConnect keynote. Thank you for my development team for sending me that code snippet. You're in trouble. But you've seen this already today. You've seen graphs being multi-model today already. How many of you guys went and visited the vendor area and saw the structure team? Yeah, lovely, lovely, friendly guys. And what structure is a graph workbench. So it's a Neo4j workbench, if you like. And apart from all the wonderful features they have around dealing with schema and metadata and blah, and blah, and blah, what structure gives you as a developer is a document-oriented graph API. That is to say, it is already possible in Neo4j to treat it as a linked set of documents. And nodes are, of course, the starting point for this, the fundamental basis of this. But it's relatively straightforward if you take an API-like structure and you read their code, for example, and you can discover how straightforward it is to work with non-graph or multi-data in the graph. Because the graph, it turns out, is the supermodel. Great t-shirt, right? And where do I get one? Does that actually work? Actually, AV guy hates this bit. You know, that's not a bad bit of photoshopping if you're at the back of the room, is it? I didn't even need Nigel Small, who was Neo's key photoshopper, to do that for me. So graphs are inherently already supermodel. Anything that you can do, anything you need to do in a document, anything that you need to do in a list or a tree, anything you need to do in a spreadsheet, you can already do in a graph. So why would you bother going to the hassle of artificially separating out these domains and fighting some kind of multi-model problem when actually, in the real world, once you strip out all of the vendor bullshit, most of the data you're working with is conveniently, oh, God, sweary Jim. He's just started, that's the floodgates. Oh, no. Why would you bother going to all of that trouble when actually this data naturally fits in the graph and it's already performant and lovely for you? So, end of rant part 1. Part 2, rant. Online and analytics. So, there are typically 2 kinds of workloads that we throw at our data processing infrastructure, at our databases. Things that we want to do rapidly in response to some user activity, so in between a web request and a web response. And things where we want to gain insight into a larger set of data, perhaps something that we're prepared to run at many seconds, minutes, hours, days of latency. I think this is really interesting. I think, again, I'm going to draw my inspiration from Karen, who was polite enough not to swear about it, but kind of brought up the idea that when you did this kind of stuff, you end up building things like cube per query. And there's I actually didn't know that it's Back to the Future Day. Would you believe that? That was like, well, lucky. Anyway, so what you end up doing in the kind of ye olde world of granddad's technology is you need to do some analysis. So you go off and do some like crafty ETL jobs and you build cubes per query and you try and predict up front which dimensions you're going to need to roll into your cube to aggregate. And it's all a little bit kind of guesswork and pseudoscience. And eventually, you've got a big expensive warehouse that you're all like terribly nervous of. The correct response to seeing one of those is that. Definitely. Why? I mean, what do you do with those things? You kind of guess up front what dimensions you need. You're going to do some aggregation. You forget a dimension, go back to square one, do some ETL. You kind of cock that up a little bit. You go back to square two. It's all just really cumbersome. And I've kind of been baffled by that. And I can't help but think that, we think about OLAP as cubes just because that's the way the technology has driven us. We think about OLAP and analytics being kind of intermingled, but they're not, right? Because the goal of analytics is to gain insight, right? It's not to build cubes. It's to gain insight into data so that we can do something actionable on it. Whether that data, whether we are gaining insight into data by looking reactively at it, so looking at the sum history of our data up till now, and using that to drive insight and drive a decision, or indeed, whether we're looking at that data and we're trying to apply it to predictive analytics. These analytic workloads are very straightforward in a graph, right? All your dimensions already exist in a graph. Graphs are naturally n-dimensional structures. In Neo4j, your dimensions are given to you by relationship types and labels and so forth. In Neo4j, you don't have some weird-ass cube thing over there that only one really, really scary SQL lady knows. Yeah? When you're doing analytics on a graph, it's just another Neo4j. It's just over there, and it's connected to your cluster, and it's got data that's in sync with the rest of your cluster. It's not some weird batch, offline, crazy, scary SQL lady thing. It's just graphs. And it turns out that graph theory is absolutely, I nearly swore again, tremendously, you know what I wanted to say then, didn't you? It began with F and ended in ucking. Tremendously good for analytics. Well, I'm like stuck in a tremendous loop now. I'm going to start saying terribly in a minute, and you'll be like, oh, that's so cute. So it's tremendously good for both reactive and predictive analytics. Now, despite Emil having written a really nice book about graph databases, the best book on the planet, bar none, about graphs is this book by Easley and Kleinberg, Networks, Crowds, and Markets. And in that book, they describe how to tame graphs to do sophisticated analyses using the almost 300 years of graph theory that we have at our disposal to gain amazing insight into technology. Because analysis isn't just about great big aggregates, right? That's like the most boring thing you can do with analytics. It's not just about great big aggregates. And I'm going to demonstrate this. So let me show you, let me give you a crash course in graph theory, because that's what you need at this point on a conference day, right? You're expecting, hey, we're just going to cruise, he's going to go blah, 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 the kind of high-level stuff. No, crash course in graph theory. Who's up for it? Hey, that's better. That's more people than knew Unix by far, it turns out. Graph theory. All right, graphs, like, they are terribly good. Who's keeping count of my curses, by the way? Because normally someone does that for me. I think I've done one so far. Graphs are really good. Graphs love triangles. It's really weird. The graph theoreticians have a really posh name for this. They call it triadic closure, like Harry fucking Potter, right? Actually, what they really mean is they want to make triangles. Graphs have, particularly graphs involving humans, so a social graph and pretty much anything that involves us has a tendency to form triangles. And you kind of observe this, actually, in your real life. Imagine this. So I am Mark Little, my ex-boss sits over there. I know Mark, I trust him, I vouch for him. Emil is my current boss. He sits over there, I know him, I trust him, I vouch for him. For the purposes of this demo, all right? Don't get too cocky. Hey. Now, the thing is, because I know and trust and vouch for both of those guys, effectively, there's a transitive trust relation running from Mark through me to Emil and back again. So it's entirely likely that at some point, because I know and trust and vouch for them, that they're going to bump into one another, and they're going to find that because I kind of dig both of them, that they're going to kind of dig each other, right? And in fact, today that has happened, which is a delight. So graph theory wins again. So that's a nice thing. So it's this nice thing in graph theory where you make triangles. And that's a really nice kind of triangle there. That's called a stable triadic closure, where I've got two sides of the triangle and the graph wants to close the third side. And in this case, it's 3 positive sentiments. Another way of creating a stable triangle is to have 2 negative sentiments and 1 positive. So let me take you to a little town in Colorado, and we'll demonstrate this. So in that town in Colorado, there's an elementary school, and there are 3 kids at elementary school, and this is Kyle, Stan, and Kenny. And you can see that Kyle, Stan, and Kenny, they like each other. They're all friends. It's quite sweet, really, right? I mean, and you can see that this is a really stable structure. You kind of feel it. Kyle likes Stan. Stan likes Kenny. Kyle likes Kenny. It works, right? It's nice. It's a stable, low-energy structure in the graph. That triangle, that triadic closure, the graph doesn't want to change it. So that's nice. That's tick. Hooray. Then we have this chap, which happens to be also my Twitter avatar. I'm a fan. What can I say? Cartman is not a nice man or not a nice kid. He's a little shit, basically. I think that's why I admire him. He's all like mixing it up, and he's a total dick, and occasionally he tries to implement holocausts. He's got many admirable qualities. But in this case, you've got a kind of weird kind of triangle here, right? So you've got Cartman, who's a friend of Craig, and Craig, who's a friend of Tweak, and Cartman, who's an enemy of Tweak. That feels a bit weird, yeah? Because, like, imagine this scenario. So Cartman really, really hates Tweak. I have no idea why. It's just one of those things. And, like, Cartman's all like, hey, Craig. Oh, man, that hurts. Tweak's such a total douchebag. Let's go and kick him in the nuts and stuff. And, like, Craig's all right. No, Cartman, seriously, I don't know why Craig's got an English voice. He just has. He's like, no, look, Tweak's my mate. Like, let's not kick him in the nuts. And it's really awkward, right? Because, like, you're kind of disagreeing there. The graph doesn't like that. The graph rejects that. It's not a stable triadic closure. It's an unstable closure, and the graph rejects it. Wah, wah, it's gone. Now, a morally awful thing would be this, where you've got Cartman and Craig, who are friends, and they both hate Tweak. Kids are shits, is what you should take away from this, because this is happening right now in playgrounds around the world, where 2 kids are ganging up on 1 kid. In terms of, like, you know, moral authority, this is a bad thing. Kids should not do this. Naughty kids. Be nice. Play nice. But actually, in terms of graph theory, marvelous. Marvelous. So it turns out this is another stable triangle in graph theory, where two people can be ganged up against one person. So knowing this is all the rules you need to know. You can now start to do some really sophisticated graph analyses, predictive graph analyses, simply by iterating over your graph, making these triangles. Believe me? Let me give you a historical example where we already know the outcome. This is Europe. It's the great houses of Europe around 1850. In fact, it's a configuration of great houses that historians call the Three Emperors League. And you can see these are indeed the three emperors involved. In this graph, the black relationships tell us allies, and the red relationships tell us enemies. So you can see that Europe was already a fairly fractious place 150 odd years ago. I noticed, just out of interest, where's Sweden? What are you guys doing at this point? Molesting polar bears? I don't know. You weren't getting stuck in, were you? Seems to be a pattern with you guys. Oof. I'm so fired. Every time I do this keynote, I know that my wife and kids are going to go hungry. It's a real problem. So anyway, here we have a graph. Now, graph theory doesn't know anything about the great houses of Europe. It doesn't know anything about history. It doesn't know anything about bantering your boss to the edge of being fired. All graph theory knows is that it wants to make triangles. It wants to make stable triangles. So let's do that, right? Let's roll this forward. Let's iterate over this. Boom, immediately we bring Italy in. It forms a stable triangle with Austria and Germany. Yeah, see that? All friends. This is Stan, Kyle, and Kenny, admittedly tooling up with artillery and machine guns, but Stan, Kyle, and Kenny having a lovely time. Great, so that's fine. And then what happens over here is, damn it, this clicker's worse than mine. There we go. France and Russia dissolve their long-standing aggravation, and actually they do this. This is weird. The graph hates this. Well, actually, no, the Brits hate this, sorry, because whoops, we used to own an empire, what can I say? Sometimes we get illusions of grandeur. So this works in terms of the graph, right? Because France and Russia, it could be like, bonjour, Russia. Do you fancy kicking the English in the nuts? And my French is brilliant, actually. Just ask my French guy, ask Julian. OK, je suis très désolé, mais je vais dire des choses maintenant. Peut-être comme ça pour moi. Merci. So the French and the Russians kind of gang up, because basically they're not hard enough to do us on their own. Yeah? Because we are, at this point, the world's only military superpower. You guys are already cacking it in case we come back over in our wooden ships. Yeah, you're like, oh my God, the redcoats are coming. We send the Canadians to burn down your... No. Wrong war. But you did burn down their clubhouse. You did. Scary sequel lady, you burned down their clubhouse. So anyway, so the Russians and the French are all like, hey, like, we're sitting in a tree, let's fuck with the English. I'm mixing metaphors, aren't I? But then, what? So this happened. This is awkward, right? This is awkward for two reasons. The graph doesn't like this. This is an unstable structure, right? Because suddenly France and the UK are friends. Now, there's a name for this. It's a famous historical document. It's called the Entente Cordiale. Now, my French actually isn't very good, but I do know the translation of Entente Cordiale. It's like, England, please stop beating us up. That's what it loosely translates as. So anyway, this is a bit weird. France and England, buddies, after so many years of the French getting their nuts kicked by the English. Weird times. But the graph does not like this. The graph refuses this. This is not stable. The graph wants that edge gone. Boom. So actually then, finally, Russia and the UK become friends. You iterate over the graph, just making these low-energy, stable triadic closures, and you end up here. This is a low-energy graph. There's nothing else that the graph wants to change. All of these are stable triadic closures. We've made triangles everywhere. Graph theory just predicted, not knowing anything about World War I, it just predicted the starting line for World War I, where we've got the good guys and the bad guys. You people, seriously, stop it. So Easley and Kleinberg have a beautiful example of this in their book. So they worked through all this, and it's just an absolutely outstanding example. You don't have to use this to predict global conflict, although it may be strangely prescient in the early 21st century that you might want to do that. You can apply this to your domain. You can apply this to figuring out what people are going to buy next. You can apply this to figuring out insurance underwriting and risk. You can apply this to a whole range of things. It's not perfect. You can still get things wrong with this approach. But actually, empirically speaking, it's actually a very, very decent way of having a good fist of a future view of how your world will be. The point here is there's nothing special about this. Once you're in graph, this is just more graph. This isn't like take your graph, drop it into a scary SQL lady cube, do some magic ETL thing, turn the handle slowly. I can't believe I'm doing an impression of an OLAP cube. I normally reserve this for dupe. This is real time. I could be here for quite a while, actually. Anyway, you get the message, right? It's slow and it's latent and it's not horrible. When you're doing this in graphs, there's no setup, there's no cubes to build. This is just the graph that you already have running on your servers. You've just got your graph and the algorithm that you want to run against it. And there are plenty of algorithms out there, written in code that you could reuse. And if there aren't ones that you can reuse directly, there are still this 300 years of graph theory research in discrete mathematics, in sociology and anthropology and so on, that you can bring to the fold when you're starting to build these kind of systems. So you just need, one graph for all of this. You don't need anything special. There's no longer one graph per query. There's no one cube per query analog. It's just your graph. It's the graph that you're using to serve OLTP queries to your web property. It's the same graph that you're running these deep analytic queries on. However, at some point, we do run up to a limit, right? You don't want to do everything in the database, right? It's that same thing where you don't want to write a big SQL job. Yeah? Sometimes you want to come out of the database and you want to use a proper programming language in order to do some compute. When you're doing really, really, really large jobs, you want to be able to bring data out of the database and compute across it, which is great. Emil talked this morning about the kind of Neo4j evolution with Spark. Having Spark having Cypher run on Spark means that you've got a really unified API to the whole graph universe. Your compute engine speaks Cypher, your database speaks Cypher, and it enables a kind of virtuous cycle where you project some subgraph out of the database via a query, you crunch it through your processing layer, and then you drop the results of that back into the graph, and you've got a continuous cycle of enrichment. In your compute sphere, in your compute cloud, you can parallelize the living daylights out of this, just as you can with other computational techniques. So in this case, then, what you've got is something a bit like this, where your app can speak Cypher to Spark, where your app can speak Cypher to Neo4j, and you've got this unified view of your underlying graph, be it compute or be it storage and query. Now, this is happening with this work going on to make Cypher a first-class citizen in Sparkland. And this is kind of, I predict this is kind of a short to medium-term thing. We're going to start seeing results from this reasonably soon. But in the future, I think there is an exciting opportunity to do this. I think there's an opportunity for some Cypher Query Planner or some other middleware to intervene on your behalf and try and figure out when it should dispatch to the database for a database query and when it should dispatch to a compute engine to crunch over those graphs in parallel. I'm not saying that Neo4j will build this tomorrow, but I think this, to me, is an obvious next step. Once you've got the unifying effect of Cypher at place, there are opportunities to do smart things, to do effectively workflows, e-science-style workflows between your compute infrastructure and your data infrastructure. I think this is a fundamentally exciting outcome. Of course, Emil spoiled it by announcing it this morning, but c'est la vie. All righty, so my final gripe. I realize I'm the guy standing between you and a cheeky beer. Yeah. I'm also the guy that knows what a cheeky Nando's is, so be nice to me. So, native versus non-native. So my colleague Max DeMasi, just like yesterday or the day before, wrote up like a stunningly good blog post about performance. And particularly, he took umbrance with vendor benchmarks. He said that it's funny that when a vendor writes a benchmark, their stuff always comes out on top. That's the TLDR. It's true, right? So that kind of got me thinking. I mean, we know how fast Neo is. Ian Robinson and his team kind of are always like beating Neo to death and seeing how fast it can go and all that kind of good stuff. But fundamentally, what struck me was Max, he happened to take umbrance with a database that was not graph native that claimed to be like a zillion times faster than everything. And it got me thinking like about the differences between native and non-native databases. And even before we get into fancy things around like cluster architecture and so on, there are some fundamental differences between a native graph database and a non-native. And it comes down to logs. It comes down to logs, it turns out. Not wooden logs, that was just my own metaphorical aid to remember what to say. But it comes down to cost of access. It comes down to big O notation. In a native graph, like Neo4j, most of the operations that you're doing in order to traverse the graph are cheap. They are big O of 1, that is constant time. All Neo4j does is chase pointers around a data structure in order to traverse the graph, and that's super, super cheap to do it. On my laptop, I can kind of spin up some vendor bullshit benchmark, and I can show that my laptop will do 14 million traversals a second, which is it's a laptop. It's a nice laptop, right? But it's just a laptop. If I was faking a graph, if I'm not a native graph database, but I want to fake a graph, I want to present a graph API to the user, but under the covers I don't have this order 1, this cheap cost to traverse the graph, what do I actually do? Well, typically I'm going to use indexes to fake this. And the thing is with indexes, they're not cheap. Neo4j, so there's a graph researcher called Marco Rodriguez, and there's a chap who used to be on the Neo4j team called Peter Neubauer, and back in 2010 they coined this term, index-free adjacency. That's what Neo has. It means that when you're at a node and you're looking to traverse to a neighboring node, there's no global index lookup there. The node itself, because of its connectivity, kind of acts like a mini index. And because of that, we can do these super, super cheap traversals. In Neo4j, we do have some index lookups, but they tend to be very, very few and far between. They tend to be to find a starting point in the graph. And once you found a starting point, you start doing this index-free adjacency thing, this constant cost operation, and you scoot your way through the graph like a little robot on steroids until you find, that's a crap metaphor, but anyway, it's stuck now, like a little robot on steroids until you find your informational goals. If you're faking it, you're doing all of this stuff in indexes typically. And indexes, they're not a bad thing, but we have to understand that the algorithmic cost of accessing an index is log. And if you have to do an index lookup for every hop through your graph, you haven't got O1, you've got log n, and that means for each hop, overall, you've got n log n complexity. And that's nothing to do with implementation detail or whatever. It's a choice that you've made when you've built non-native kit. You're going to fake the relationships by doing index lookups. And oh, by the way, if you want to traverse in both ways, you're going to need 2 sets of indexes, and that has an impact on your write performance as well. So Max rubbished these this kind of non-native guys, because ultimately it boils down to this. Order 1 and a few log n is always going to be cheaper in any reasonable production graph of size millions or billions than looking up in indexes. Sure, that you can publish benchmarks all you like, where you take a tiny fucking graph and then say, oh, my database is faster than Neo4j, the world's leading graph database. And then you will be caught out because computer science. This is University of Sydney. I used to be a lecturer at the University of Sydney. The students were not this happy when I was there. They were like well more pissed off. Anyway, because computer science wins out. If you've got to do n log n costs for your traversals, you will lose out to any native database which can do this in n order 1 steps, period. Computer science wins out. So that's for a single database. A native engine is going to be, by computer science, well, that was a bit like Thundercats, wasn't it? By computer science, I decree that native technology wins out over non-native. But what about now when we're going to cluster these things, right? Because eventually we want to put this stuff into production, and we want to do some clustering. My old boss has just perked up. He's like, this is my stuff, Padawan. You better represent me well. All right, boss, ex-boss, current boss, I'll represent you brilliantly too. So there's a really interesting thing going on in distributed systems. There is a significant tension between having a system which is available and having a system which is reliable. Now, available means that even in the presence of faults, the system will be able to accept reads and writes. It doesn't mean that you'll get the correct answer from the system. It just means that it will be available for reads and writes. Reliable is the property of a system where even in the presence of faults, you give the correct answer. And you can't have both. So back in the day, Fisher, Lynch, and Patterson wrote their famous paper, it's now called FLP, which demonstrated that you cannot have both. Thanks, Mark, for nodding. That's very generous. I know that I'm treading on your toes here. You can't have both. You can have availability or reliability. You can be somewhere on that spectrum, but when your bozo architect tells you, I want exactly once guaranteed delivery of messages, and you say can't be done, he'll be like, well, you're crap, I'll hire someone who can do it. No, can't be done. FLP says it cannot be done. You have to make trade-offs. So there are interesting design trade-offs when you're clustering. And a lot of the NoSQL databases, they're definitely towards the availability end of the spectrum. That's a big thing for them. And that's cool. It's cool. But the thing is in the graph world, things are a bit more difficult. We need consistency in the graph world. We need, actually, if you're going to do graphs and you're going to allow bidirectional traversal, you need actually to have consistency of 2. Consistency of 2 is hard. It's not like just twice as hard as consistency of 1. It's like 1,000,000 harder than yeah, it's another algorithmic thing. You guys might not have it over here in your posh universities, but that there, million is pretty important to us. So you've got to be able to keep 2 sets of replicas in sync. And if you don't, bad things happen, especially if you want to do 2 ways. Now, Julian, I'm sorry, but can we do that thing again? Because this is going to get really horrible for you again. Sorry, dude. I'm really grateful that you would come to this conference and suffer this abuse, but let's see what happens. Don't worry, you guys are coming. You guys are coming. Let's see what happens then if we try to fake up a graph in a non-native database. So here I have some document store or column store or whatever, and you can see that I've kind of got 2 records, and they have some referential integrity with respect to one another, right? So you can see that the United Kingdom loves the United States. And you can see here that we've got, from our point of view over here, we say that we've got a relationship called loves. It's in an outbound direction to record 0. Over here, this is record 0. It's the USA. And we can see that USA agrees that it has a loves relationship from record 1 in the inbound direction. So no matter which way you traverse this graph, you will definitely find that the UK loves the US, or you will find that the US is loved by the UK. This is a safe position, right? Because we don't want to be drone striked. Thank you. Now, happy days, right? We love you, you take care of us, we think we've got a special relationship, you giggle at us behind our backs, but it's okay, it's okay, it's okay, we accept that, it's part of the bargain, right? We did pay you back our Marshall Plan money, by the way, in 2006. Yeah, we never renege on a debt. Now, talking about countries that do renege on their debts for the Marshall Plan, bonjour la France. What would happen if you got some, multi-threaded access to this system? What would happen? What if we're over here? What if one thread is over here, kind of changing this left-hand side record, saying that we really like the Americans 100%, USA, USA. I don't have the accent for that, do I? Anyway, you get what I'm saying. So we're over here changing this record, and meanwhile, the perfidious French are changing this record here to kind of get us in trouble with you guys. What happens? Which of those changes is authoritative when they're run concurrently? Anyone know? No, I don't either, right? It's completely non-deterministic. We could be anything. So what happens here is the graph becomes non-deterministic. It's like if you traverse the graph one way, it's like, hey, the UK loves America, don't nuke them. If you traverse the graph the other way, it's like, wait a minute, those limeys don't like us anymore, let's nuke them. This is a bad thing when you want to generally avoid being nuked by your allies, right? You guys get the fallout, right? It blows straight across the channel and poisons you as well. Thank you very much. You've ruined it for everybody now, naughty France. So there's a funny thing about graphs. For graphs, reliability, the ability to answer the question correctly, is far, far, far more important than availability. So if you pushed me, if you needled me and said, Jim, are you giving up reliability or availability? I'd say, look, dudes, under pathological failure scenarios, I'm going to have to become unavailable, because to do anything else will cause immediate corruption, which is really surprising. Because the whole of NoSQL has been about availability. It's not my kid. I can kind of get away with this. It's kind of funny, right? But if that was my kid, I'd be like, oh, you guys are mean. So, but there are already databases out there that are doing this. And surely they must work. No, I'm afraid they don't. Right? They will lose your data. The honest ones actually write it on their web page how they will corrupt your data under normal operations. And I salute them for being honest. But you can't use them safely. Which brings us to the point, so what is Neo4j doing about it? Fair question, good friends, fair question. So we kind of, so Ian Robinson and I wrote a book without Emil, but with a guy called Savas Parasitidis called Rest in Practice. So Ian and I were really interested, and Savas was really interested about large-scale distributed systems. So it's a pretty interesting topic to be involved with. And we kind of got to think what it meant to be web scale. And we got to do a lot of thinking about why the web scales. And really, we actually got together last year at GraphConnect, actually. We haven't all been together for ages, right? So it was really nice. That's a horrible picture, isn't it? Hang on, just a sec. There's like a filter option, right? There we go. There we go, that's much nicer to look at, isn't it? So we got together at GraphConnect last year, kind of reminiscing. But it's really interesting, because you're kind of shooting the breeze with those guys and like, you know. Oh, hi, Emil. Yes, you did write a book too. Just 1 minute. Where's that filter key again? Far better. Right, there we go. So we kind of shot. See, I told you this was going to be a dick move, right? It's like the guy was so gentlemanly this morning, I'm just like South Parking him. So we got to him, we're talking about why does the web scale the way it does? Like, is the web scale all about having massive amounts of hardware and like being all googly? It's like, well, no. The web scales because it federates load through the network. That's what it does, right? The whole protocol is designed to federate load through the network. And it's not about having like, 10,000 machines serving 1 million concurrent users, because that's not web scale, right? That's exactly 100 scale, which is a lot less than the web, because the web is like several billion scale. So we kind of think, yeah, that's really cool. That's really cool. How do we take that kind of, we're definitely influenced by the Unix philosophy, but how do we take our influence of the web philosophy and direct that towards building, better ways of making native graph clusters? What Emil didn't announce this morning, mostly because he doesn't understand it, is that from Neo4j 3.0, we have a web-like clustering protocol, where we have an architecture that the engineers call Core Edge, but my marketing team will soon give us a more humane name for it, where we have a relatively small number of machines in the core of your network. They can be geographically distributed or co-located, that's your choice. But these machines are like the data citadel. They own your data, they keep it safe. They are reliable. They don't lie, they don't serve stale data. They are reliable. In fact, they are coordinated by a protocol called Raft, which is written by local boy Diego Ongaro from Berkeley, now at LinkedIn. And in that core, we've got a model whereby when you commit a transaction to Neo, that transaction is guaranteed, safe, and replicated. When you've got an ACK back, that transaction cannot be destroyed other than by act of God, wiping out your whole data center and all of your backups. However, federating that load outwards, like the web does, we have a bunch of machines that we call edge machines, because they live at the edge of the network. And those things are caches, but they're not just like dumb memcache-style caches. These are fully functioning Neo4j instances, which means you can run graph queries on them. And you can put them locally, you can spread them around the world, you can do whatever you like. So we've got this notion now where we can federate load out through the network. The keystone of this is Raft, right? Raft means your data is safe. Those core machines are provably safe. The Raft guys have done a brilliant, brilliant job with that protocol. I love Raft. Compared to Paxos, it's a doddle. We have a Paxos implementation in Neo4j today. It is scary hard. When you look at Raft, the protocol itself is humane. And that's an important thing, right? The understandability of Raft means there are very few places for bugs to hide, and bugs in distributed systems are difficult. So we like Raft. So that core is kept safe by Raft. Once you commit, you get an ACK, and your data is now safe. Why? Well, because Sweden, right? Sweden's the most boring country on the planet, except Canada. All they do is figure out ways of being safe. That's their job. A Volvo, it's not a car. It's an airbag delivery system. Brum, brum, pff. Marvelous, marvelous. And that's important, right? Because if you can't trust a database to keep your data safe, you have no business putting your data in that database. Yeah? You don't poke your fingers in unknown holes and not expect to have them come back bitten by some critter. Databases are the same. You entrust us with your data. Your data's important. Your business is run on it. So the very least we can do is not corrupt it. We not lose it. So, actually, all joking aside, thanks, Sweden, for being the world's second most boring country, because you've instilled Neo4j with a sense of safety, which is critical for our users' data. That's the last time I'll say nice things about Sweden, I promise. So, given, though, that we've got this core cluster and these edge machines, and you can say, hey, Jim, but these edge machines, they seem to be eventually consistent with respect to the core. And you just said that was a bad thing. Well, could be, except in Neo4j 3, we will also give you the ability to read your own writes, which is a really, really nice way of reasoning about your data, right? So suddenly you can write things into the core, you could read your writes from an edge at some point. And the way that we plan to do that is using the Neo4j Bolt protocol, which happens to be a fork of message pack that's just twice as fast. Well done, remoting team, good job. We're going to use something, again, looking for inspiration from the web, we're going to look for something like HTTP's e-tags, such that when you do a read, you'll be able to say, at this transaction level or greater. And if the transaction hasn't percolated over to you yet, you just get pause for a moment until that happens, which gives you the ability to do things like write core, read edge, which is nice, right? Because the ability to read your own writes makes reasoning about your use of the database really straightforward. I'll write stuff, and then I'll see it. Now, I can't tell you how bloody hard that is as a distributed systems person, right? Read your own writes. But HTTP already tells us how to do it simply. You're using e-tags, we can do it on the web. Using the equivalent of e-tags, we can do it inside the database cluster. It's very easy to reason about, and it's not terribly expensive either, right? You'll just get pause for a moment until the transaction reaches the machine you've read from. But we can actually go further. Actually, we can go further. We can even choose to give you linearizability in this cluster, which is practically the holy grail, right, for databases. So we can give you, choose your consistency when you query, when you read the database. We can allow you to read from any machine, so read from any edge. We can allow you to read your own writes from core or edge. We can allow you to read the leader. There's a special role, not that special, there's a role in Raft called leader, which tends to be the most up-to-date instance. Or indeed, we can perform linearizability by getting you to query a quorum of the core machines. And once you do that, yes, it's relatively expensive, but you can get linearizable semantics from this. So in those cases where you absolutely positively need linearizable, you've got it. That's pretty sweet. And we're going to Raft all the things. We are not going to give you a choice on the write channel, however. On the read channel, you're going to get to choose your consistency. Most of the time, you'll probably pick conservative consistency levels because Sweden. On the write channel, you don't get to pick. We are going to Raft all the things on the write channel because Raft keeps your data safe. So once you've got an ACK back from Neo, it means that your data is now committed around the cluster. It is safe. And in Neo4j terms, that also means, by the way, durable on disk. So we suffer partial failures. We just bounce back from that. You guys don't get to detune that. You don't get to turn that off. That's our prerogative. So where are we then, ladies and gentlemen? I just read, I'm like 0. This means you guys need beer. Where are we? Graphs are the supermodel. They already do all of those things you're thinking about. You're thinking about doing documents, it's a graph. You're thinking about doing trees, it's a graph. You're thinking about doing hierarchies, it's a graph. You're thinking about doing lists, it's a graph. It's like the Admiral Akbar, it's a graph. Ah, that's awesome. So this multi-model stuff, it's a sideshow. I don't care what Gartner says, this is a sideshow. Graphs are the big game, multi-model is a distraction. You want to do polyglot? Great. There are databases that do one thing and one thing well. Glue them together. That's what we do. It's the 21st century. Cypher on Spark is game-changing, right? You've now got a uniform graph API to the two fundamental pillars of the data ecosystem. So Neo4j to your storage and query graph, and to your graph compute. And that's going to evolve brilliantly. That's going to be such an exciting place to live in the future graph space. And finally, once you've got a safe Raft, you can start to build amazing superpowered clusters. And so Neo4j itself is going to continue to evolve. We are going to continue to evolve past that. But you'll have to come to GraphConnect London, and I'll tell you all about it then. So just finally, suffices me to do that, and wish you lovely people Pass on to you lovely people my sincere thanks for coming today. It's been wicked cool hanging out with you. It's now time for us to go and have a couple of cheeky beers. I hope to talk to many of you then. Thank you for coming to GraphConnect. It's been fantastic hanging with you.